Thank you.
Yeah, so great. So then we have our next speaker, Tess Smith, or Schmidt, who is who is a Luis Alvarez postdoctoral fellow in the computing sciences at the Lawrence Berkeley National Laboratory, and is interested in connections between neural networks and physics. I guess her PhD was in physics, and she also has a very cool blog with various interesting materials, atomic architects, and so on, a team that she's leading. So it will be very interesting to hear her talk about unintended features of Euclidean symmetry in equivariant, Euclidean symmetry equivariant neural nets.
Great, thank you, Edgar, so much for the introduction, and thank you to the organizers for organizing this wonderful workshop and for having me, and thank you to all the speakers for preparing such wonderful talks. It's been really cool to see the combination of computer science interaction with mathematics and physics, so I'm really enjoying the workshop, so thank you all. So today I want to talk about a different symmetry group than maybe we've touched upon it, and I guess Taco maybe touched upon it in his talk a little bit, as well as some of the other talks. But I want to talk about Euclidean symmetry and how when you implement this symmetry into neural networks, you sometimes get some unintended features from doing this. So I do want to add that please feel free to ask questions during the talk. My goal is to be understood, and so if there's any way that I can make any additional clarifications on the spot, please feel free to ask the question. I'll do my best to look at the Q&A. Edgar, please feel free to say, hey, Tess, look at the questions. There's a relevant question you should answer now, just in case I'm not able to multitask as well as I'd like. Okay, so yes, we're going to talk about Euclidean symmetry equivariant neural networks, but I also could have easily given this talk another title called All I Wanted Was 3D Rotation Equivariance, and what I got was geometric tensors, space groups, point groups, selection rules, normal modes, degeneracy, second order phase transitions, and a much better understanding of physics. So just another reason maybe to use equivariant neural networks is that, especially when you deal with some of these more involved groups, they really test that you understand the question you're asking. So hopefully I'll be able to elucidate that a little bit more in the rest of this talk. Okay, so symmetry emerges when different ways of representing something still mean the same thing. And in the context of 3D space, we have Euclidean symmetry because we have the freedom to choose our coordinate system. So let's say I have these 3 molecules, they're in 3D space. It's still the same set of 3D molecules in space, regardless of whether I choose the lower coordinate system or the coordinate system on top. It's still the same thing. And that's where this symmetry, this Euclidean symmetry, emerges from. And I also want to notate the difference between the symmetry of the representation, so how you're representing a system and what are degenerate ways of representing the system, versus the symmetry of objects that exist in this representation. So symmetry of 3D space means that I can choose my coordinate system in any which way I like. And the way that we do this, oh yeah, sorry, I should probably, let me specify a little bit more what I mean by Euclidean symmetry. So the way that we can transform between these degenerate coordinate systems that for these physical systems that mean the same thing is through 3D translation, so just moving in 3D space, 3D rotation, and then inversion, which is basically take x, y, z to minus x, minus y, minus z. It's a little hard to actually show, but maybe a more intuitive way of thinking about it is that you're probably familiar with mirror symmetry. Our hands are symmetric via mirrors, roughly. And to get mirrors, you need inversion and rotation. So the twofold rotation and inversion. So that's the Euclidean group. So first of all, let me just make sure that I've stated that clearly. Okay. So now let's talk about the symmetry of 3D space and then the symmetry of geometric objects. So let's take a single benzene molecule. A single benzene molecule is highly symmetric. It looks the same under specific rotations, translations, and inversion. In this case, it's not translation because I'm just dealing with something that's kind of you can define a center of mass. You can define sort of a unique origin, but I can rotate it. It's got a 6-fold rotation axis, and it's got several mirror symmetries as well as 2D rotation axes. So benzene itself exhibits many symmetries, but the reason why we're interested in Euclidean symmetry is fundamentally because of this issue of coordinate systems. So let me take a moment to kind of elaborate and define the meaning of invariance versus equivariance for things that are in 3D space. I'm going to do this with the example of a vector. So invariant quantities do not change with rotation, translation, or inversion. Or they're invariant with respect to some of those operations. And then something that's equivariant means it changes, but it changes deterministically. So we understand what the transformation would be. So if I have a 3D vector, I have a magnitude, so that's the orange kind of bar. I have a direction, which is the pink arrow, and I have a location for this vector, which would be the purple point. And these different quantities, or these different properties of the vector, transform differently under rotation, translation, and inversion. Magnitudes, so basically the relative distance between two objects, for example, is invariant under translation, rotation, and inversion. So that's an invariant quantity under all Euclidean symmetry. Now, the direction of a 3D vector is invariant to translation because the direction is still the same, but it's equivariant to rotation and inversion. Whereas if I just pick a point in 3D space, it's sensitive to all of these operations. Okay, so there's sort of 3 different approaches for making models symmetry aware with 3D data. And I'm going to talk about this sort of in the context of representing atomic systems because that's the problem that I'm most interested in applying these types of models to. So again, we have our benzene molecule and we can represent it in terms of coordinates. So just 3D coordinates, 3D space. And coordinates are the most general, but again, they suffer from this issue that they're sensitive to translations, rotations, and inversion. And so there's sort of 3 different approaches that kind of emerge. So you can do approach 1. If I want to train a model that maybe learns gets to learn properties about the benzene molecule or similar molecules, I could do data augmentation. I can just show it a bunch of rotated versions of molecules. I could basically try to mod out all this coordinate stuff that's very troublesome and come up with some invariant representation, something that's saying, oh, I have, 6 carbon atoms and 6 hydrogen atoms. It has these types of bonds. I could try and come up with some sort of invariant representation, or I can say, okay, if there isn't, I need a model that just fundamentally handles my data type of geometric coordinates. So in my personal experience, these emojis are to kind of symbolize how I feel about these relative approaches. And today I'm going to focus on equivariant models. I do want to give a quick note about data augmentation. So in our experience, to get sort of the angular resolution that you need for a lot of physics problems, you need about 500-fold augmentation just to deal with rotations. And so that's not necessarily handling, you get handling inversions and mirrors and things like that. And one of the issues, especially when you're applying for physics applications, is that data augmentation doesn't guarantee that your operations are equivariant. It just kind of gives you a sense that you have rotation equivariance emulated in the data. And for physicists especially, they really like to understand what's happening every little bit. And so this is one advantage kind of for the community and why we like dealing with equivariance rather than data augmentation, just because then we reliably know that this operation is being applied in the same way to things that are sharing local symmetries. So I just wanted to put that note there. Okay, so how do Euclidean neural networks achieve their equivariance? I want to just say that Euclidean neural networks is kind of a blanket term for several different works. So tensor field networks, Clebsch-Gordon nets, 3D steerable CNNs, and kind of their descendants. And I've just put some names here for some of the relevant folks in this area. Certainly not all, but if this is something of interest to you, I highly recommend looking at all these people's papers. It's a really cool field, and people have written some really nice papers on this stuff. Then there's one primary open source implementation of Euclidean neural networks and that I've worked on, as well as one of the first authors from the 3D steerable CNNs paper, and it's Mario Geiger, and that's E3NN. And technically speaking, that implementation is the only one that has parity included, so inversion symmetry. Okay, so how do these networks work? So Euclidean neural networks are very similar to a convolutional neural network. They're a subclass of convolutional neural networks. And the main difference, the first main difference is that the convolutional filters are restricted to be of a particular form. So rather than some general argument W, or sorry, some general function W of the argument r vector, which is the distance between 2 points. So rather than just an arbitrary function of space, we restrict it to be separable into a radial and an angular component. So we learn the radial component, but we take the angular component to be spherical harmonics. And the main reason for this is that, well, the mathematical reason for this is that spherical harmonics are the basis functions of what are called the irreducible representations of rotations and inversion. But kind of said in a more, I don't know, in a simpler manner, spherical harmonics have some really nice transformation properties under rotations. So for example, if I represent some signal as a linear combination of spherical harmonics of a given rotation degree L, so L is kind of, you can kind of think of it as an angular frequency. So how much does it have to rotate to sort of look the same? So if you have something with L equals 2, you can do 180-degree rotation, and it kind of gets back to where it started. So if I start off with a signal that's in a given frequency L, and I perform a rotation, it stays within that frequency. And this property is really nice for sort of organizing your features and also for encoding equivariant operations to act on those features. So that's the first difference. The second difference is actually a consequence of this filter choice, and that everything in your network is no longer just some scalar array of, or you might call it a tensor, but it's no longer just scalars, they're actually geometric tensors, which have very, very specific transformation properties under rotation, translation, and inversion. So this means we can no longer get away with just scalar addition, scalar multiplication. We have to replace all those operations with their tensor equivalents, so tensor products and direct sums. And to give you maybe a flavor of what these operations look like, if I ask you the question, how do I multiply 2 vectors? There's many answers I could give you. I could say, well, a vector times, I could dot a vector with a vector and get a scalar. So a vector is one data type and a scalar is another. I could take a vector and I could perform the cross product and get another vector out. So it's yet another operation. And then I could also perform the outer product. So I could get a matrix from 2 vectors. And so the general geometric tensor product generalizes this procedure for specifically geometric tensors, so data in 3D space. And it actually, the nice thing is that it allows you to contract these indices, so you don't just keep acquiring indices as you go throughout your network. So while I'm representing this matrix as sort of having 2 indices, using what are called Clebsch-Gordon coefficients, we can actually contract these indices into a single index. And it's not just a Cartesian index, it ends up being an index over these different spherical harmonics, or things that transform like these spherical harmonics. Okay, and then just maybe to make it a little bit more concrete, the input to these types of networks are going to be some sort of geometry, so some sort of signal in 3D space. And you can think of that as like points in 3D space with features living on those points. So it's very similar. You can apply this to image data as well as point data, but you can think of these as kind of graph convolutional neural networks with edges that are featurized by radial distance vectors, and a very, very specialized kernel and interaction rules. So you can think of it that way. So the important thing is not only do we give it geometry and features, we also order those features in the same representation that we're using for our filters. So we actually will specify with what rotational frequency certain features have. So in the case of, let's say, this little coordinate system, I have a little coordinate system, and I have 2 masses, and they each have an acceleration and a velocity, and they have a little mass. I would encode the masses because those don't change with rotation. I would encode those as scalars, which have angular frequency of 0. And I would encode the vectors as having an angular frequency of 1, because if I transform the coordinate system, I transform the vector with that coordinate system, versus if I have features that depend on like x times y, those are going to change with twice the angular frequency because you have both an x and you have both y. So that's just to give some kind of intuition. And higher rank or like more complex tensors, like 3x3 matrices, will actually transform, different components will transform with different angular frequencies. And yes, so again, this is these angular frequencies between the spherical harmonics and how we're representing our data. These are the same frequencies. These are all just representations of the same irreducible kind of platonic ideals of mathematical data types in these models. Okay, so that was sort of how it works, but what does it get you and why is this useful for physics? So let's say I have a molecule and I would like to predict forces on this molecule. Maybe I'm doing it in a molecular dynamics simulation. If I've trained my network to predict accurate forces on one molecule, then I can give it a rotated copy and it will predict exactly the same forces, just rotated. So we get an equivariant prediction, guaranteed. And additionally, because especially in these types of data surrounding physical systems, you end up getting a lot of similar local motifs like you would in images. These networks have been shown to generalize very well to similar systems with similar motifs. Okay, another one that's closer to sort of what I did my PhD in. So I worked on crystal structures, and the way we represent crystals, which are sort of, we treat it as infinite systems, is we take a box, we fill that box with atoms, and then we tile that box everywhere in 3D space. But one of the issues with this representation is there's no unique way to represent a crystal, either in orientation or in the shape of your box. And so one thing that's very important for doing applications for solid state physics is that you want to be able to represent these periodic structures, and you don't want your model to be sensitive to arbitrary ways that you chose to define your unit cell. So in this is silicon. If you zoom in, you'll see little atoms that are forming all these little tetrahedral structures. And there's the primitive cell, which is sort of like the most concise way to express a crystallographic pattern. Then there's sort of the conventional unit cell, where it's most easy to see all these different rotation symmetries and translation symmetries and things like this. And then there's supercells. So you can even have like versions of the representation that are like too expressive. They don't need to show that much, but you can have it anyway. And what's nice is that you get the guarantee that these networks will treat these crystals in these different settings in the same way. And then a really big payoff is that these networks can predict very complicated geometric tensors. So on the right, I'm showing a water molecule that's being rotated. And then, or sorry, on the left, I'm showing a water molecule being rotated. And then on the right, I'm showing a matrix that describes the interaction of the electrons of water between the different atomic orbitals. And so this matrix, you can just look from the rotation. While, you know, the water molecule, it looks pretty reasonable how it's rotating. You're like, okay, yeah, it's something you probably learned that. But learning all the intricacies of how the different components of this matrix transform, you can definitely do it, but it would require a lot more data versus if I just train a network on a single example of this, an equivariant network on a single example, it can extrapolate to these other rotated versions. And that's really useful, particularly because many physical properties are these more complicated geometric tensors. Okay, so what about those consequences and what about those features that you kind of get from doing this? So one I sort of alluded to already, really when we originally were doing tensor field networks, which is one of the first papers on these types of networks, we really just wanted 3D rotation equivariance, so we didn't have to do data augmentation. But what we found out is that if we wanted rotation equivariance, it came with geometric tensors. And so this is really interesting because we didn't realize that we wanted that. It sort of was a consequence of wanting something else. And what's nice is that geometric tensors are the data type of physical systems, and they have many forms, and any physical quantity you can pretty much express as a geometric tensor. I've yet to find an exception to the rule. I welcome anyone to give me an exception to the rule. I haven't been able to figure one out. So if we take the example of like a 3x3 matrix, so I can represent this, you know, kind of as a grid of numbers, but I can also express it as a linear combination of spherical harmonics, and that's what I'm picturing on the left. And so this kind of implies, well, not only can we give numerical geometric tensors to these networks, we can also give shapes. And these networks will inherently understand kind of the symmetry of these shapes and what that means. Furthermore, just kind of maybe some less intuitive data types that arise in these systems. There are 4 different vector-like quantities in 3D space. The vector that we're all kind of familiar with, the pseudo vector, which is pretty much the same as a vector, except if I invert space, it doesn't flip. This is what you get from cross products. So if I take this vector cross this vector, or this vector cross this vector, I get the same. Or if I invert space and do the same thing, I get the same pseudo vector. Double-headed rays, turns out they have slightly different transformation properties that you can rigorously encode into your inputs. And things like spirals, which They don't have inversion symmetry, but you can flip them by 180 degrees and they still look the same. So that's kind of cool. This is a big one. So it turns out that if you have any equivariant network, this isn't just for Euclidean networks, this is for any equivariant network, the outputs of the network will have equal or higher symmetry than the inputs. And this is known actually in the physical sciences as Curie's principle. And this was stated around 1894. And this is not Marie Curie, this is her husband Pierre. So this statement can be kind of summarized saying when effects in a physical system or in something show certain asymmetry, this asymmetry must be found in the causes that gave rise to them. Basically saying you can't get asymmetry from nowhere. And to give an example of this, if I give a Euclidean neural network an input like a tetrahedron, and I'm going to take 3 differently randomly initialized models, so 3 different randomly initialized models, what you can see is that the outputs preserve this symmetry. And the only thing I gave it was that I gave it a tetrahedron. I didn't tell it, hey, I'm giving you something with tetrahedral symmetry. I did that implicitly by just giving that as inputs. And the same thing if I give it an octahedron, these are the same models. Now it'll give something with octahedral symmetry. Another way of putting this is implement group equivariance and you get all subgroups for free. So things like space groups, which are extremely important for describing crystal systems, and point groups, which are very important for describing molecules. Turns out you don't need separate networks for these things. Your data basically forces the network to give outputs that are compatible with that symmetry. Here's another example or another consequence of the outputs having equal or higher symmetry than the inputs. And you can kind of use these models as symmetry compilers because they can't fit something that doesn't symmetrically make sense. So imagine 2 tasks. Let's say I give one of these, I give these networks 4 points in the shape of a rectangle. And I ask it to articulate displacements for these points to make it into a square. And then I'm going to ask the converse. So I'm going to give it a square and ask it to deform to a rectangle. And what you find is that it can do the first task because you're going from something that's low symmetry to high symmetry, and it can't do the second task. And inherently it's because the rotation equivariant network is going to be like, well, what do you mean? Which rectangle? There's 2 of them. There's 2 different rectangles that symmetrically look the same under rotation. So if we train a neural network to actually make these predictions and articulate these predictions, not just as vectors, but as these kind of spherical harmonic shapes, these blobs, you can kind of see what's actually going on in the network. So on the left, we have it predicting something perfectly. The reason why it's a round blob is because I'm only including up to a certain number of spherical harmonics. Taco kind of mentioned that spherical harmonics as a basis is really good for representing some things, but representing really sharp things, you have to go up to very high number of basis functions. So I'm just going to a limited number of basis functions. In this case, I believe it's up to L equals 6, so 0 through 6. So that's why it's a kind of a blob shape, but you can see it overlaps with the orange circle, and so it's doing a great job. But on the other side, what's happening is that the network is predicting degenerate outcomes. Again, it's basically saying, well, either you're making a rectangle in this direction or you're making one in this one. I can't differentiate which one you're actually predicting because you didn't give me enough information. So I'm going to predict the average of both possibilities. And this is super interesting because this is very physically relevant. This happens in nature all the time. Okay, yeah, so basically you get a symmetry compiler. By making an equivariant network, you get subgroup symmetries. But what's even cooler is that because we have a neural network, we can actually find the data that's sort of missing from our inputs, finding the data that's implied by saying, well, this input should lead to this output. And it's like, well, no, it doesn't. That doesn't symmetrically make sense. But you can use the gradients of your loss. So you say, okay, well, you should have predicted this. And it's like, I predicted this. You can use the gradients of that loss with respect to the input to basically back out what symmetry breaking input you needed to, what symmetry breaking input that you needed for it to be able to learn the tasks. So in this case, we initialized our network with inputs that were just ones, single ones. And ones, which are scalars, have the same symmetry as a sphere. So it starts off as each point has a feature that could be imagined as a sphere. And then what it does is it learns to make a sort of oblong shape. And what it's basically doing is it's picking out, the X direction and the Y direction are different. And so once you make that distinction in the data, it can perfectly fit the task. Okay, how am I doing on time? I think I'm about done. So yes, so I want to give a big thank you to the developers and collaborators of E3NN, which is the repository that I work on and use in my own research for Euclidean neural networks. I want to give a shout out to my co-authors on the tensor field networks paper. And then I want to do a quick recap. So 3D Euclidean symmetry is rotations, translations, and inversion. And the reason why it emerges is because different coordinate systems can describe the same physical system. So it means the same thing, even if we write it down numerically in a different way. And Euclidean neural networks are neural networks that are equivariant to these operations. And the way that they achieve that is through specialized convolutional filters, geometric tensor algebra, and something that I didn't cover but is also necessary is you have to make equivariant nonlinearities. And this equivariance can have unintended features. So we have symmetry-specific data types, which is extremely relevant to the physical sciences. And then your output symmetry is equal or higher than your input symmetry. And this has various uses. And last but not least, we can use these models to sort of infer what symmetry might be missing or what data might be missing to break certain symmetries. So if you have any questions, feel free to reach out to me. And I'm just going to put these resources here for papers if you're interested in these types of neural networks, links to the code, past talks, and some books on group theory in case you're interested specifically for Euclidean symmetry. So I'll take any questions.
Great. Thank you very much, Tess, for a very lively and informative talk. And so there's one question from audience member Talent regarding practical use of the EC3NN code. If my input is and output is a scalar volumetric data, then can we use higher order representations that correspond to vector or tensor field in hidden layers and get reasonable predictions?
Yeah, so I'm good. Let me interpret that first to make sure I'm getting the question right. So you're saying, okay, if your inputs and output, so your inputs and outputs are scalar, and so you're kind of asking, what do you get from, do you get anything from using higher order representations in your intermediate layers? And the answer is yes, especially if the interactions of your system kind of actually are implicitly doing these sorts of interactions, and particularly if you have geometry. So if you have geometry in your system, that's inherently an L=1 feature. And so you can have different combinations of that geometry to lead to higher order terms. And we actually, the paper that I'm showing, so E3NN on QM9, that archive number, that actually gives a really nice explanation of how that can help even predicting some scalars in the QM9 data set. Thanks for the question.
Yeah, thank you. So I actually had just one quick question myself. So what do you feel is possibly like the most, maybe like one of the most significant kind of scientific problem that this technology can enable us to solve that we weren't able to solve with previous technologies? Like this may be like too vague, but I'm just wondering if there's like a concrete problem, like I can predict, I don't know, something, but yeah. Yeah.
So I mean, I'll just put these up here just in case any of these words catch people's eyes. I don't know if there's like one in particular. I think part of it is that I think these provide a really good framework for thinking about scientific problems in a neural network framework, checking your data types, checking your assumptions. So I think it's a very useful tool. I'm personally very excited to see what this will do for predicting like electron charge densities. So if you know where the nuclei are in a system, solving for where the electrons are at is computationally really hard. The algorithms that we currently use scale anywhere from n to the third to like n to the 9. So it's not very tractable for high precision. So I'm very excited to see what we can do with networks in these problems, but there's so many other interesting problems too. So I don't know what the best one is, but I like that one.
Okay, great. That's very helpful. Yeah, thanks for explaining that.